When we look out into the vast, expansive, awe-inspiring cosmos, there are innumerable stars out there. Yet, one of them dominates our sky and our lives, burning brightly and ferociously at the center of our solar system, the Sun. It's easy to see how generations of humans before us were inspired to create all kinds of legends to explain its mesmerizing glow. Now, as technology has advanced beyond the realms of their wildest imaginations, we can delve into the processes within and around our neighboring yellow dwarf, going deeper than ever before. As we journey through its ferocious atmosphere, let's explore what I'm sure you'll agree are the fascinating phenomena that materialize there. I'm Alex McColgan, and you're watching Astrom. In this video, I want to dive into the Sun, drawing on different wavelengths of electromagnetic energy to showcase the star in a new light. Previously, we've explored Jupiter and some of its moons through the lens of the electromagnetic spectrum, which you can see in this video here. Today, we will be revisiting this approach, but this time, rather than a planet, it'll be adapted to investigate a highly energetic ball of plasma. The light we'll be looking at is old. Although light is the fastest thing we know, the image of the Sun that we see from Earth is approximately 8 minutes and 20 seconds old, meaning we are viewing what the Sun looked like a few minutes in the past. And if you count how long it takes the photons generated within the Sun's core to make their way through each layer of the Sun before escaping into space, the light that reaches us is anywhere from 10,000 to 170,000 years old. Where to begin? Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the Sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory Satellite, or STO, a NASA space mission launched back in February 2010. STO aimed to better understand the solar variations that influence life on Earth and our technological systems by studying the dynamic solar surface and atmosphere at different electromagnetic wavelengths. By looking at light beyond the visible range, NASA was able to pick out normally invisible details crucial to our understanding of the Sun. This image was taken using a 19.3 nanometer wavelength, representing light found in the extreme ultraviolet region. At a wavelength corresponding to a color temperature of 1 million Kelvin, we can clearly see the higher region of the Sun's corona. Interestingly, the Sun's corona can also be seen by the naked eye on rare occasions, such as during a total solar eclipse. When the Moon is perfectly aligned between the Earth and the Sun for a fleeting period of time, the view of the central, brighter disk known as the photosphere is fully blocked, revealing a radiant exterior. While this is a breathtaking view already, the corona is still nowhere near as detailed as it is in this image taken by the STO. This makes it a useful tool for scientists' studies. Let's go a little deeper to features of the Sun just beneath the corona. At a color temperature of 20 million Kelvin, the intensely vivid spots indicate events known as solar flares. Here is some footage of a particularly busy week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They're colossal explosions where the Sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the Sun itself, from which the fields ultimately originate. But they are not the only feature of the Sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the Sun, are another fascinating feature which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma which are magnetically open, meaning that rather than forming closed loops that go back to the Sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with the Earth's magnetosphere, beautiful aurora lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the Sun's outer layers. Non-visible spectrum light is an incredible tool, and there are so many different features in the Sun's outer layers to look at. There are solar filaments, also known as solar prominences, the large loops of plasma that rise from the Sun's surface. These enormous loops are large enough to make the Earth look like a tiny speck and can stretch hundreds of thousands of km into space. They can form in as little time as a day, but a stable prominence can remain in the corona for several months. In this example, we watch as a prominence snakes its way out of the photosphere and into the Sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly the Sun's intense magnetic fields are causing this material to move. One fact you might not know about the Sun's atmosphere is that sometimes it rains there. Not all of the charged plasma fired into the Sun's corona continues out across the solar system. Some remains in the corona, getting trapped and cooled, until it falls back to the sun's surface as a shining rain. This coronal rain is beautiful to look at, but is best observed from a distance. It's still millions of degrees in temperature. Of course, falling gently back to the sun's surface is only the fate of some of the sun's plasma. This is where the comparison to Earth fails. After all, on Earth, the clouds do not crack like a released elastic band, firing into space. On the sun, thanks to tightly wound magnetic fields, they do. This is a time lapse of a coronal mass ejection. Watch as the structure forms at the bottom left of the sun for some time before eventually snapping and sending billions of tons of plasma out across the solar system. Even with the Earth's magnetic field, being hit by a powerful one of these could be devastating for our satellites and electrical grids. All these structures are imaged by the STO here utilizing a 30 nanometer wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the sun, alternating around an 11-year solar cycle, which I just did a video about here. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the sun's corona. Taken over the same time period, the following two images use two different wavelengths of light. The first, imaged at a color temperature of 600,000 Kelvin, depicts the quiet corona and features coronal loops. The second, imaged at a color temperature of 2 million Kelvin, displays the much hotter active regions of the corona. The stark comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events, and we still haven't technically made it through the sun's atmosphere yet. Moving further inwards, let's look at another image produced by the STO utilizing a 160 nanometer wavelength of light, this time of the transition region. The transition region is a layer which sits between the sun's corona and the chromosphere, the lowest layer of the sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting from Kilauea in Hawaii is 1170 degrees Celsius or 1443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter. Traveling even deeper, we find ourselves immersed in the sun's chromosphere, which is the last layer of atmosphere before we reach the sun's surface itself. Imaged here using 170 nanometer ultraviolet light, it is estimated to be approximately 1,700 kilometers thick. Closely inspecting the chromosphere, we identify some mesmerizing features known as spicules. Swaying like long, wavy grass blowing in the wind, these long jets of plasma shoot upwards from the sun's surface at speeds up to 100 kilometers per second, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers, over 1 kilometer taller than Mount Everest. Forming and vanishing in around 510 minutes on average, the processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the sun's magnetic fields at that level. That is until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the sun as they didn't think they affected the motion of the magnetically charged particles, but once they were added, it transpired that the neutral particles gave the magnetically charged particles the unexpected buoyancy they needed to escape the sun's plasma and shoot up into spicules. Descending further through the sun's lower atmosphere, we eventually reach the photosphere, the surface of the sun itself, which is best imaged using visible light. While the edge of the photosphere appears sharp and precise, as it often does to our naked eye, this is simply due to how far away the sun is. The sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid or gas state in any region of the sun, it can only be plasma, referred to as the fourth state of matter and estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed, solid boundary of the sun, unlike what the image may suggest. And sadly, it is the deepest layer of the star which scientists can measure directly. At a closer look, you may notice some dark spots on the left and side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures, but that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here, heat becomes trapped beneath the photosphere due to decreased convection within these areas. When comparing this image of the sun to a previous one taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Now let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth and using a wavelength of visible light of approximately 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells which don't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 km wide and are known as solar granules. Consider them the top layer of a churning convection cell underneath. Brighter areas inside each granule represent fluid of unimaginable temperatures rising from within the sun's upper interior layer to its surface. Upon reaching this boundary, the fluid has nowhere else to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough, dark boundaries surrounding each cell before repeating the cycle. This process closely resembles the convection currents within the Earth's mantle, responsible for driving plate tectonics. This process is no joke. While on average it is estimated that each granule lasts for as little as 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 km per second, generating waves on the sun's surface due to sonic booms. Fascinatingly, these granules can also be seen in the full disk view we saw earlier, utilizing the same wavelength of visible light. You may think that this image looks quite grainy for such a high-X space probe. And you're right, it does, but that graininess is the granules on the photosphere of the sun, not a processing effect or excess noise in the image. And that's it. Sadly, our journey ends here, as scientists have not yet figured out how to image deeper into the sun using either visible or non-visible light. Much of what lies beyond this layer remains shrouded in mystery. But we can see the benefits of using light of all different spectrums in our study of the sun. They help us to observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots and shape-shifting cells, just to name a few, in completely new ways. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these imaging techniques. Maybe one day we'll find ways to see deeper, using techniques we can barely dream of currently, just like those ancient generations of humans long ago could hardly dream of the methods we're utilizing these days. But for now, just knowing there is so much going on unseen in the universe and knowing we have the means to uncover it fills me with excitement and curiosity. Who knows what else might there be out there, waiting to be found? Have you ever wanted to see some of these features of the sun with your own eyes? Obviously, it's dangerous to stare directly at the sun without protection. But there is a time approaching that you'll be able to see the sun's corona unhindered and unaided by any telescope during the massive total solar eclipse on April 8, 2024. When that day comes, you'll need the proper eye protection. Today's video was sponsored by Visisolo, a provider of NASA-approved, ISO-compliant eclipse glasses that let you safely admire and take photos of the rarely glimpsed sun's corona with your own two eyes. Visisolo's eclipse glasses are made in the US, and their products come either singly or in combo packs, which are perfect for the whole family. Visisolo also has an innovative smartphone photo solar lens that allows you to safely take pictures of the sun. Get ahead of the game by buying yours now. If supplies run out and you miss this eclipse, there won't be another one in the US until 2044. So, click on my link in the description below, or use my code to get a 20% discount coupon on your next purchase. Go check it out. Thanks for watching. Want to learn more about our sun's corona? Check out this video here. A big thanks to my patrons and members. If you want your name proudly displayed at the end of each Astrum video, check out the links below. All the best, and see you next time.